So today we're going to get a bit more depth into friction. So we dealt a little bit with friction at the very beginning, showing the very basics of it. Today we're going to go, as I said, more detail into how friction actually works and some more complicated scenarios. So obviously in basics, friction resists any motion. So if I'm pulling on this box, for example, I'm just going to be some frictional force that opposes that motion. So in this case, going to the left. Friction comes about through two surfaces in contact. So the contact between this box and the floor is what causes that frictional force. Again, tangent to the surface, opposing the motion or the possible motion. And so other forces that are acting on this box, because they're important as well, are the weight of the box itself. So generally at its center of mass, I have some weight. Then I have some normal force. If I'm not pulling on this box yet, so if there's no force P here, if there's no force P, then there's no force F as well, because F is going to oppose that. If there's nothing pulling, there's nothing to oppose. So without any P and without any F, I also have this normal force that pushes up, probably again, right at the center of mass. But then what happens is because I'm pulling this box at some distance h above the floor, I'm not only causing a force to the right, I'm also causing kind of an implied moment. And so what happens because of that is two things. Number one, I get this frictional force, so equal and opposite force due to friction. And then it also causes this normal force to actually move towards the front of the box due to this rotational motion. So still not pulling hard enough for this box to move at all. So again, frictional force equal and opposite, nothing's happening in terms of motion left and right, but this normal force does move to the right. And the amount it moves, I can find by taking the moment around that point. So I'd actually find how much it actually moves. And so there's a few complications with friction. One of them being, is this box going to move or not? And the other one being that this box doesn't necessarily only have to move. There's also a possibility that the box can rotate. So instead of sliding, if I pull with a force P that's larger than my frictional force, it's going to slide to the right. But even if my frictional force is equal to my pulling force and I pull hard enough, I may be able to get this to rotate around this bottom right-hand corner. So the box basically tip over. And so that kind of happens, again, if I'm pulling with some force P, assuming I have a lot of friction, this force N is going to move to the right. And the harder I pull, the more force P I put on it, the farther this thing's going to move. If it moves past this front corner, that's when it's going to start to rotate. That's when it's going to start to tip. In general, my frictional force can be related to the normal force through the coefficient of friction, mu, and there's two types of that. There's the static version and the kinetic version. Static version, usually a little bit larger than the kinetic version. It takes a little more effort to get something to start moving. And then once it's moving, it takes a little less effort. And that's, again, due to the fact that once it's moving, I'm using the kinetic version of the coefficient of friction. Before it's moving, I'm using the static version. And then in addition to those differences, there's also differences between certain materials. So again, friction comes about due to the interaction between the two surfaces. So is it metal on metal? Is it wood on wood? And all sorts of different combinations give you all sorts of different values of the coefficient of friction, generally found through experimentation. But basically some things are easier to slide over than others. And so if it's easier to slide, smaller value of mu. So again, looking at my box and starting out pulling with a certain force, again, starting out with a small value and increasing it gradually. At first, my force is not strong enough to overcome friction, so nothing's going to happen. My frictional force is going to be equal and opposite to P. I'm also assuming that this thing's not tipping. So again, I'm assuming that my frictional force and P are not large enough so that N moves past this front corner. So because I'm not pulling enough to overcome friction, I'm also not pulling hard enough so that friction equals mu s times N, because mu s times N is actually the maximum possible friction force. Once I go slightly above that, it's going to start to move. But anything before that, it won't. So if I'm going anything less than that, this thing's not moving, and my frictional force is just equal and opposite to P, not necessarily mu s times n, but rather some value that's less than mu s times n because P is less than mu s times n. If P gets up to the value of mu s times n and just slightly over it, then this thing starts to move. My frictional force, instead of being mu s times n, drops down to the kinetic version, mu k times n, and then that's what the forces are as it moves along. So again, once I get beyond that value of mu s times n for the value of P, box begins to slide. I then have this frictional force mu k times n. And then again, whatever happens after that with my P's and F's, I now know those values. Again, mu k values, generally 20, 25% less than the corresponding static values. So essentially my box is going to accelerate. I have some value of P that's at least 25% bigger than F. And so that's going to be an overall force to the right, and this box is going to slide. A third scenario that we've seen, or that we can see due to friction, is a situation where it's very unclear whether the object's going to move or not. So kind of in the previous case, it was a little unclear. This situation with the ladder, it's actually even more unclear. I could have some frictional force, some mu value between the ladder and the wall. Same thing for the ladder and the ground. This ladder probably has some weight, has some angle. And a lot of times it's not going to be obvious, is this ladder going to slide? Is this enough frictional force to hold it up or not? And so whether it slips or not, it's going to depend on a whole lot of things. As I said, the coefficients of friction, the angles, the weight. And so a lot of things that depends on whether it slides or not. And so we've essentially seen three scenarios at this point. We've seen the easiest case, which is there is actually motion. So you know that your force P is bigger than the maximum value, mu s times n. If your pulling force is bigger than friction, it is going to move. And then you know it's going to move. And you also know that the frictional force is mu k times n because it's moving. It's a dynamic case. And so that's the easiest case because you know the most things. You could have no motion. So my box is not moving. P is less than that value of mu s times n, so it's not enough to actually pull it to the right. I'm also assuming it's not enough to make it tip over. That's the case is a little harder because you don't technically know what the frictional value is. It's not mu s times n because P is not that high. So again, a little harder because you don't actually know what the friction is in that case. And then the unknown case, this case of the ladder, because there's even more things that you don't know. So as I mentioned, first case is the easiest. If you have motion, then your frictional force is just mu k times n. And simplest scenario there. The case of no motion is a little harder because you don't actually know what your frictional force is. All you know that it has to be less than the maximum value, which is mu s times n. So in this case, friction becomes one of your unknowns essentially. So when you do your statics analysis, so if this is a 2D scenario like we've seen on the previous slides, 2D scenarios, you have three equations of equilibrium: force in the x direction, force in the y direction, moment around some point. The frictional force F just becomes one of your unknowns for the problem when you do statics analysis. So you can find it through the equations of equilibrium. And then the hardest case is if there's motion or not. And so we're not going to see too many of these in this class because this class is statics. If it's a statics class, that kind of assumes things are not moving. And so we're generally going to stay in that no motion case. But this is useful for later classes, namely dynamics class. Dynamics class, sometimes you know it's moving, sometimes you don't know if it's moving or not. And in that second scenario, the best way to go about it is with this procedure. So we assume it's not moving basically first. If you assume it's not moving, you can then use statics equilibrium equations to find all your frictional forces. And then once you found that frictional force, you can compare it to mu s times n. And then if it is less than mu s times n, then you did everything right and your box is not moving. If it turns out that by doing that, you find that a frictional force is bigger than mu s times n, means that what you assumed, namely that the box is not moving, is not true. And so basically at that point, you can restart your analysis, knowing that it's moving now though. And so knowing that the frictional force is mu k times n, and do the analysis that way. And so last thing you want to deal with in friction is wedges. So you can use wedges to transform forces into much larger forces or adjust heavy loads, such as this situation here. So I have some large, big weight, and I want to move it up using this wedge by pushing it to the right. If I can leave this alone, so if I stop pushing on it and this wedge stays here, then it's called self-locking. So basically the frictional forces are stopping it from sliding out to the left. So that's called a self-locking wedge. There also could be a scenario where this weight is heavy enough to push it out. If I'm not pushing on it, in that case, it's not self-locking. So analysis for these wedges generally involves breaking the two pieces apart. So you have some wedge and there's also some weight that you're trying to lift. If you think about the free body diagrams of each object, so all the forces acting on them. So my wedge, as I'm pushing my wedge, I have some force P. There's going to be some normal force N3 pushing up, holding that wedge from going through the floor, some frictional force opposing the motion of P from the ground. And then it's also going to be sliding against this wedge. And so there's going to be a normal force, basically the wedge pushing down, sorry, the block pushing down on the wedge, as well as some contact frictional force. So again, frictional force parallel to the surface of interaction, which is up at this angle, normal force perpendicular to it. And then going up to the block itself, equal and opposite forces. So the block pushes down, N2, causing some frictional force, F2, equal and opposite on the block from the wedge. Wedge pushes up, some force, N2, causing some frictional force, F2. And then that also pushes the block towards the wall. And so there's a normal force from the wall and possibly some frictional force from the wall as well, acting on that block up top. So it could have up to 7 unknowns in this scenario. I have this possibly unknown applied force P. So I might be trying to find how much force do I need to actually push this wedge up. And then I have 3 unknown normal forces, N1, N2, and N3. 3 unknown frictional forces, F1, F2, and F3. A lot of these scenarios, the weight of the wedge is ignored because the wedge is usually much smaller than the big heavy block you're trying to lift up. So in that scenario, the weight of the wedge is fairly irrelevant, at least compared to this big weight up here. If it's not a big deal. Just put the weight of this wedge in there as well, which you'd probably know. So it's not necessarily an unknown. So total of 7 unknowns. If I look at what I have here, I have 2 free body diagrams in 2 dimensions. So each free body diagram in 2 dimensions for each individual object gives me 3 equilibrium equations, usually. But in this case, it's actually only going to give me 2 because there's no motion, or sorry, no rotation involved. The wall and the floor are basically stopping any rotation. So that's what these normal forces are doing. So because of that, there's really no moment equations, mainly because I'm not necessarily sure exactly where these normal forces are acting along the bottom and along the side and along this side as well. So moments aren't that useful for these equations. So really what I have is 2 equations of equilibrium, forces in the 2 directions, x direction and y direction, one for the big block and one for the wedge. So that's 4 total. And then my frictional forces and my normal forces are related because I know that frictional force is coefficient of friction times the normal force. And so that gives me 3 more equations relating all these unknowns. So grand total there, 7 equations. So 7 equations for 7 unknowns. And that gives me how to solve those problems essentially. So those are the types of problems we'll be solving later in class today. So I'll see you all then.